So this is going to be the second part of the notes for the next test. This is basically going to be continuing with stoichiometry, but now we're going to do stoichiometry with different kinds of reactions, specifically a lot of precipitation stoichiometry and solution stoichiometry. Okay? So let's recall that water is the common solvent. It's actually sometimes called the universal solvent because water is such a good solvent. Pretty much a lot of things, anything ionic, not anything, most things ionic will dissolve, and so it's actually really, really hard to keep pure water because things dissolve in it so well. The reason that water is such a good solvent is because it is polar. Water is polar. Write that down. It's right there. You can underline it, but write it down again. That is what gives water so many of its properties. It behaves differently than a lot of other things. It's one of the only things that I am aware of that is actually less dense in its solid form, which is why ice floats, because it's less dense than its liquid form, and it's the way that the structure goes together when it's solidifying. And of course, that's the reason it's polar, is because there's an uneven distribution of the electrons. Remember, the hydrogen is less electronegative, so the oxygen holds on to the electron that they're sharing more, making it polar. Okay? We'll talk a lot about that when we get to bonding. Okay? That's just all the things I just said. Okay? Normally we have the bond angle. It's talking about how it's a little bit less than what you think it is because of the lone pairs on the oxygen. It pushes them down. And then you can look at the pretty pictures in your notes. Okay? Hydration, remember, is when we will, when water surrounds something, we call it being hydrated. And then solubility is depending upon what you're trying to dissolve in there. So like NaCl is highly soluble, while silver chloride is not soluble. Remember those solubility rules from Chem 1? They're back. When we did double replacement reactions? Yeah, well then you're going to relearn them, or learn them for the first time. I don't know. So this is an important particle diagram. Remember, I told you particle diagrams are really important in AP Chem. This is a very good example of how we draw something when it's being hydrated. So you won't have to draw it that nicely. That's a computer model, but you will have to draw that at some point. And the main thing is when you're drawing the ions, what do you notice about, okay, so you had sodium chloride over here before it was hydrated. It breaks apart, and now it's being surrounded by water molecules. What do you notice, first of all, about the anion and the cation?
There's one of each.
No, there's not. There's more than one of each. I don't care about the numbers of each on the anion. What do you notice about the difference between the anion and the cation? The anions are bigger. Thank you. That's what I was looking for. Remember, anions are bigger than their parent atom, and cations are smaller. Okay? Which one are the cations? Come on. Thank you. Thank you. Thank you very much. They are positive. Okay? And the reason that they are smaller is because they've given away their electrons, and so now there's more of an uneven polarity between the nucleus and the electron clouds. Okay, so you want to always draw the anion bigger. These are notes you should be making, by the way. Draw the anion bigger. Okay.
Wait, why is the cation smaller?
Because it has lost electrons, and now you have more positive nucleus pulling on an electron cloud that has less negative charge. Okay. So the anions are going to be bigger because they now have more electrons and they have protons in the nucleus. Okay? When we get to bonding, that'll make a lot more sense, but for right now, just draw the cations smaller than the anions. What do you notice about the water that's surrounding the two? They each have, they're drawing them with 6 around there. You just can't see around the cations, are small.
The charges.
The charges. Look at the anions. What part of water? Remember, water looks like this. When we're drawing water, we have the H's, and then this one is slightly negative. These are slightly positive. So, whoops, I don't like this stylus. It's like sticks to the thing. Okay. So we've got the slightly negative up here, slightly positive. So around the anion, what's lining up with the anion?
Positive.
The slightly positive. Okay. So this part of water is attracted to the anion. Okay. And then the cation, which is positive, has this part attracted to it, surrounding it, okay? Because opposites attract, right? Okay. So make sure you make note of that. When you draw the water, you want to draw it oriented in the correct position around whichever it is, a cation or an anion, okay? Okay. Hope you made notes of all that. Hint, hint. Okay. So now you're going to draw one formula unit of magnesium chloride surrounded by water molecules. So I'm going to pause the video at this time and let you do that. Okay, you should look roughly something similar to that. I didn't do my fourth water molecule here. Okay? So, first of all, one formula unit of magnesium chloride is MgCl2. So you should have drawn one magnesium cation with the 2+ charge. Okay, and then you should have drawn 2 chlorine anions.
But it all had to be like connected. Yeah.
Oh, what happens when I put an ionic into water?
It's not.
It breaks apart. It wasn't connected in the last slide, right? We had them separate. Because when you dissolve an ionic compound in water, they dissociate, if it's soluble, and then they break apart, and they're no longer connected. If I was drawing a molecular compound, say like sugar, I would keep that as all one molecule. Okay, but an ionic compound, when it says formula unit, they're telling you it's an ionic compound. Also, it's a metal and a non-metal ionic compound. So if it's soluble in water, they break apart. They bust up, and then they're swimming around individually surrounded by water. Okay? All right, let's keep going. What was your question? I usually do 4 around each one. The magnesium had a +2 charge because it's a group 2 metal, so when it ionizes, it's a +2. Just usually draw at least 4. Sometimes they will tell you in the problem, draw 6 water molecules or whatnot. So the oxygen was attracted to the magnesium because the oxygen of water, that part is slightly negative. So it's going to be attracted to the positive ion, whereas the hydrogen on water are going to be attracted to the anion. So they're, yeah.
So is it alright if you just drew like actually draw the molecule, you just drew like the O and the H's?
I mean, yeah, but usually if it's on a particle, draw particles, not the letters. Okay, so water can dissolve non-ionic substances as well, such as alcohols and sugars, among others, and then especially if they're polar, what it can't dissolve is non-polar things, and then it looks a little bit different. So in this case, we have ethanol, and so then we show you that whenever the water is attracted to it, so ethanol has an OH group on it, and so the water is going to be attracted to the oxygen from the water to the hydrogen on that ethanol group. Okay, and so that's how that would be able to be dissolved. Okay, so that's how you would draw that. Okay. Remember, fats do not dissolve in water because they're nonpolar. That's why, like in Italian salad dressing, the oil is on the top because it's less dense. And then you shake it up, and then as soon as you let it sit for a while, it separates again because oil and water don't mix. Like dissolves like is a useful tool for predicting, but it is not an explanation. I never want to see you write like dissolves like on an AP paper. That is something that we use to help ourselves remember that. But we don't ever say that. You have to have an explanation. And then when we get to bonding, it would be an explanation of how their interactions, don't work or do work or whatever. But you don't ever say like dissolves like. Some of the things that we'll say in here are for things to help you remember them, but they're not an explanation. Okay? So just remember that. You're going to have to address electrostatic aspects, which we'll get to when we get to bonding. Solution, of course, is a homogeneous mixture. Remember, you can have all kinds of solutions, not just solid and a liquid. You're sitting in a solution right now. Air. Okay. Okay. Yeah.
Are we part of the mixture?
No, you're surrounded by a solution right now. Yeah, you're surrounded by a solution. Okay? In a solution, the solute is what is being doing the dissolving. So like if I was to put salt in water, water would be the solute. No, it would be the solvent. The solute is what is being dissolved. The solvent's always in the bigger portion. And water is the universal solvent, right? Okay? If it ionizes 100%, we call that a strong electrolyte. If it has some ionization, then we call it weak, and then if there's none, then it's a non-electrolyte. And you recall that electrolyte means it can conduct electric current, okay? When we're talking about electrolytes, all your soluble salts are strong electrolytes, and your strong acids. Please add those 3 that got left out of your notes. Those are the 6 strong acids. Memorize them. There's 3 of them listed, and for some reason the other 3 were not listed, and I didn't catch it till I sent that out to print. Those are the 6 strong acids. Memorize them. Okay? It is HCl, HNO3, sulfuric acid, hydrobromic, hydroiodic, and perchloric acid. Those are your 6 strong acids. Okay? Any other acid is weak. Any other acid is weak.
Why is hydrofluoric not strong?
Hydrofluoric?
Yeah.
Ah, that's a very good question. We get much greater detail when we get to bonding, but the hydrogen-fluorine bond is incredibly strong, so it won't break apart very easily. It doesn't mean it can't hurt you. Hydrofluoric acid is actually very harmful to human tissue, but in terms of ionization, it does not ionize very much, and it's because the bond between hydrogen and fluorine is really, really strong. And it has to do with size and the great difference in electronegativity. Because recall, fluorine is the most electronegative, and so it really holds on to the hydrogen, whereas the other ones are more easily broken apart, which has 100% dissociation. Don't confuse pH with strength of acid. You can have a weak acid and still have a really low pH. Okay, that's the difference. The strength of an acid purely has to do with, does it dissociate 100% or does it not? Doesn't have to do with its pH. Okay. Strong bases also completely ionize, and the strong bases are going to be all of your group 1 bases, and then group 2 from calcium down. Okay, so in other words, beryllium hydroxide, magnesium hydroxide are weak bases, but from calcium down in group 2 are strong bases. Memorize that too. Group 1, yeah, if it's in red, you have to add it in. Group 1 bases are all strong. Is hydrogen considered part of a group 1 base? Please tell me no. Yes, hydrogen is not part of group 1. Remember, hydrogen and helium are up there by themselves, they're oddballs. Okay. Remember, bases taste bitter and feel slippery like soaps are basic. Okay. Yesterday when you were doing the lab, if you were able to smell that ammonia smell, that's a weak base. Ammonia is a weak base. Okay. You have to memorize all of the acids. I needed you to add those other 3 in, and then you memorize the strong bases. But I mean, just look over there and go group 1 and then calcium down of group 2. Okay. Anything else is weak. So if I had aluminum hydroxide, that's a weak base. Okay. Here's the weak electrolytes. They're only slightly ionized. You'll get to know those really well when we get to the acid-base unit, because we have to do a whole other kind of calculation to get their pH when there's slight dissociation. That's like one of the hardest units, by the way, not till next semester. But acetic acid, for instance, is what's vinegar. It's diluted. Obviously, it's not strong. It's not pure acetic acid, but it only ionized about 1%. So, and it still has a really strong smell. Composition of solutions. Before we get into the types, let's remember molarity. Some of you already figured that out when we did our little group quiz. Y'all put your little minds together and got that. But remember, it's number of moles over liters of solution. Liters of solution. Okay? Okay. Wait, what?
Oh, never mind.
Okay? It's already written down. You didn't have to write this down. Okay? Something that I want to bring up, you may not see it right away, but you will at some point. You'll see something called millimolar. It's written there, but basically it makes our calculations a lot easier, and it's moles of solute over milliliters of solution, and we call that millimolar. Okay, we don't usually report things in millimolar, but we can use that when we get to our equilibrium calculations, and they're giving you like small volumes. It's easier to do a millimolar and then not have to do like decimals. So I didn't want you to say you've never seen it. You've seen millimolar. Okay. This is going to be in here twice because this is important. I'm going to do it fast the first time. How we prepare solutions of a known concentration. We dissolve it in a small amount of water. That right there is called a volumetric flask. Okay, we dissolve the whatever amount of solid we need in a small amount. We get it to mix up, and then we fill it with water to the mark on the volumetric flask, because a volumetric flask is made to be exactly that amount when you're at that little white mark, and it's usually in the neck. Okay, I've got a bunch back there. I've got all different sizes. I've got cute little 25 milliliters that are adorable, and I got 2,000 milliliter ones. Okay, but the reason what you don't want to do is you don't want to fill it up with water and then put the powder in. Why? When you got finished, would you be at that exact mark?
Like you wouldn't know how much.
Oh, you wouldn't know how much.
It takes up some space, right? Because it's liters of solution. It's not liters of water. It's liters of solution. So if I need exactly 1 liter, and I fill it to 1 liter and then add solid into it, that takes up space. Now I have more than 1 liter, so I don't have my exact amount. Okay, so that's the key on that one. I'm going to say it again in a minute because this is important. I'll put it in there in a minute. All right, calculate the molarity of a solution prepared by dissolving 11.5 grams of solid sodium hydroxide in enough water to make 1.5 liters of solution. Something that I would have to do all the time when I'm making up solutions for y'all is this. Okay, so I'm going to start with my 11.5 grams of sodium hydroxide. Going to divide by the molar mass of sodium hydroxide, which is 40. And then I'm going to divide by 1.5 liters. And you can do it all in one step, or you can break it and do moles and then over liters. I care not, whichever way you want to do it. But you should get 0.192 molar. Big M is molarity. When you see big M, I want you to immediately think moles per liters, because most of the time when you see the big M, that means you're going to convert with it. Okay, you're going to do something to convert with it. Okay. All right. Next one. Exercise 2, I'm going to let you work on your own because that's easy. The next one is a very important concept. I'm going to stop for a little bit because even though I show you this, people will still make this mistake a lot. Okay, so don't be those kids. Don't be those kids. Okay? All right. So if you have a formula that has a subscript, you have to multiply your concentration by that. Because when it dissociates, just like what I did a while ago, I had MgCl2. When I drew it, I drew 1 Mg and I drew 2 Cl2s. So my concentration of Cl is going to be twice as much as my magnesium. Okay? And so, for instance, if I have, and go ahead and show it dissociating. Nitrates are always soluble, so we don't have to worry about that. So when it dissociates, it breaks apart, and I get cobalt 2 plus 2 nitrates. That's the way it dissociates. So if the original amount was 0.5 molar, this is going to be also 0.5 molar, but this one is going to be 1.0 molar because I have this 2 right here. Okay, so it's twice as much. Because when that breaks apart from 1, it breaks apart to 1 cobalt, 2 nitrates. So my nitrates is twice as much swimming around in solution. Okay. Please don't say swimming around in solution on an AP exam. I use a lot of those things and give human qualities to they don't do it on your test. Okay? They won't like that. Okay? So the next one, I have Fe iron 3 perchlorate. So Fe3 plus 3 perchlorates. So if this starts out at 1 molar, right, this is going to also be 1 molar, but this will be 3 molar. 3 times as much because of that 3. Okay? So please get that in your brain because that trips up kids every year multiple times. Okay? And it doesn't seem like that hard of a concept, but when you go to do it, you forget. Okay, especially if they back ask you a question about the original and say, what about this? And you forget that, oh, for that concentration, it was twice as much nitrate, or it was 3 times as much whatever ion. Okay, so, and then, we good so far? If I'm going too fast, slow me down. Okay, this is just one to help you remember. Remember, I told you you're going to use molarity as a conversion factor, but if you will just memorize in your head that volume times molarity gives me number of moles. Okay, and if I'm doing a stoichiometry problem, I need to get to number of moles so that I can use my mole ratio to get to the product. Okay, so volume times molarity is number of moles. Conversely, if I wanted to get liters of solution, I could take my volume and divide by molarity as well, or my moles and divide by, you can flip that. Remember, you can take that conversion factor. I can either do moles per liter, or I can flip it and do liters per mole. Okay, and it's always per how many liters?
No, 1.
1.
What's 22.5?
That's the molar volume of a gas. Yeah, but if you're talking about a molarity, it's always moles per liter. Moles per liter. Moles per liter. So if I tell you something's 0.5 molar, that means it's 0.5 moles of solute in 1 liter of solution. Okay? All right. Calculate the number of moles of chlorine ions in 1.75 liters of 1.0 times 10 to the negative 3 molarity molar of zinc chloride. Okay? So volume times molarity will give me moles, right, Tyler Moss?
Yes.
You just appeared on the video. You can do it as a crisscross, or you can do it as just a regular old calculation. It's up to you. So my liters cancel out, right? And then for every 1 mole of zinc chloride, I have 2 moles of chloride. Do you agree with that? All right, so then my answer becomes 3.5 times 10 to the negative 3 moles of chlorine ions. If you prefer, I can put grids back in there. Just like to show you both ways. It's the same thing as grids. The railroad tracks, or whatever you call them. So you can do it either way. Zinc chloride right here. For every 1 mole, you get 2 moles of chlorine. Okay? All right. Any questions on that? Does that seem pretty straightforward? Yes. Okay. Blood serum has 0.14 molar of sodium chloride. What blood volume contains a whole milligram of sodium chloride? Okay. So first thing we need to do is how many moles is in 1 milligram of sodium chloride? Okay. So I cannot stay in milligrams, can I? So that would be how many, whoops, didn't say I was going to, how many grams would that be? Oh, no. I need to divide by 1,000, not multiply, okay? So I'm going to say 0.001 grams of NaOH divided by the molar mass, which is 58.44. Now I'm in moles, so what can I use as my conversion factor? Say? What'd you say? Say it. Oh, I thought you said, you're right. Yeah. So I'm going to say 0.14 moles per liter, right? And it doesn't ask us what volume, but because we're dealing with milligrams, we're probably going to go ahead and put it back in milliliters, so it'll make more sense to us. So 1,000 milliliters in a liter, and I get 0.12 milliliters of blood contain 1 milligram of salt. Any questions on what I did? Does it make sense to you? It's all about the units. Just follow the units. Good? Yes.
Wait, where did at the bottom of the answer right here?
Uh-huh.
What's the 1.7 times 10 to
Oh, that's how many moles. Contains that many moles.
the? Oh.
I just kept going. They stopped, because it didn't ask us to solve for moles, but they did just so you could get there. Like if you were to stop at this point, like just divide .001 divided by 58.44, it would be that answer of 1.75 times. It's just stopping you along the way. We just did it all at once because we are talented. No reason to stop for coffee. Okay, I told you it was important, so I'm going to tell you again. Preparing a standard solution. I'm going to do it a little bit more detailed here just because you need to know the words to use, like use a volumetric flask, use a pipette, that kind of thing that's listed here. So it says you have a massed or weight amount of solute in a small quantity of distilled or deionized water. Either, you don't have to say distilled or deionized, just pick one of them. You don't want to use tap water. You're going to dissolve it by swirling, and then if it is a liquid that you're making, like you're making it, diluting it, you're going to use a pipette, okay? And then you add additional water, and you say until you reach the mark on the volumetric flask, okay? And then secure and invert and mix, okay? I just said all that, what's on there, okay? Here's a picture of what that would look like, so you can see, because it's important.
That's solution.
That's how you make solutions. That's exactly how I make solutions for labs. I go in there and do this.
Solution is on this page. It's like-
Yeah. Okay. So here we're going to measure how would we make this, okay, of potassium dichromate. How much must be used to make 1 liter of a 0.2 molar, okay? So volume times molarity gets us to moles. So we're going to say 0.200 moles per liter. We want 1 liter, right? So that's that and that. So now I have moles of potassium dichromate. How do I get to grams? What do you say, Jason? Molar mass. And where do I put that, top or bottom? Top. Yeah. So I will give you the molar mass. I'm not going to make you calculate that. The molar mass is 294.2 grams per mole of potassium dichromate. So I would need, that's 3 sig figs, so 58.8 grams. Oops. So if I were to go into the lab to make this up, I would get my balance, and I would get my little weigh boat. I would put 58.8 grams into my weigh boat. Then I would put that into a little bit of water in my volumetric flask, shake it up. It's a real pretty yellow color, actually. Shake it up, and then I would fill into that mark, into where it is. And every volumetric flask, the mark's in a little bit different place because those are hand blown to be calibrated to that amount. So sometimes the mark's way down low in the neck, sometimes it's way up high. You just have to look for each one, okay? And then the best practice is fill it up, and then when you get close, you go to the squirt bottle. Because if you're trying to pour and land on the mark, you're not that good. None of us are. I mean, it's just easy to overfill. So when you get close, you use the squirt bottle and just get the mark, okay? Okay, now we're going to talk about dilution, okay? M1V1 is equal to M2V2. M1 and V1 are going to be your initial molarity and volume. They're always going to be bigger because they're going to be your concentrated. This is how I make acids. We buy acid in concentrated form because it's easier to store, and then I dilute them. By the way, if I'm diluting them, how do I do it? Add acid to water. That's a sidebar, okay? So in this case, when you're doing that, you're going to use a measuring pipette. There's 2 kinds. There's graduated measuring pipette, and there's volumetric or transfer pipette. Volumetric are more accurate. They're just like a volumetric flask in that each pipette that's volumetric only delivers that amount of volume. So if it's like a 10 milliliter, it's got a mark in the neck, and you fill that pipette to that 10 milliliter, and you're delivering exactly 10 milliliters. You will probably use some graduated pipettes in here. They have markings. So I have a 10 milliliter graduated pipette. It's got markings that I could deliver 1 mil, 2 mil, 3 mil. They're not quite as accurate. Okay. If I'm doing a large dilution and I need like 250 milliliters of stock solution to make up a lot of acid, then I would use a graduated cylinder because I don't have a 250 milliliter pipette. But if you're doing very, very small volumes, a pipette, okay? The most accurate, write this down, it's not here, but the most accurate thing for delivering volume is a burette. Okay? That's going to be the most accurate, so if that question ever popped up. If you remember doing titrations, the burette was what we titrated with to deliver volume. B-U-R-E-T.
So the College Board asked that question?
So what they might do is indirectly ask it and like give you some equipment and say, here's some equipment, what would you do to find this calculation? And you would say what, yeah. So burette is, you're always going to use burette for titrations, yeah, unless it's a micro titration. Okay, dilutions, we already talked about that. Same kind of process, you would deliver the thing and then add the water to the mark. Again, you would still like get some of it to mix in before you filled it all the way up. Okay. You would not, again, put some in there and, you don't want to overflow. Leave some space. So what volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of 0.10 molar H2SO4? So let's do that. M1V1 equals M2V2. And we are solving for V1 because we know how much of the diluted we want to form and we know what the molarity of the concentrated is. So we're going to say V1 is going to be equal to M2V2 over M1. So 0.1 molar, 1.5 liter over 16 molar. That's going to give me 0.0094 liters or 9.4 milliliters. Mostly I would put that back into milliliters because I don't have, all my glassware is usually in milliliters. Yes?
So how do you know if you're supposed to use like that formula that you did? Is it if you're trying to find like the original?
Yeah, it's always going to be for dilutions.
Okay.
So it's already going to be it's going to give you similarities. Yeah. So in the other one it said we want to make this molarity, but how much solid do we start with? Okay. So then we would just do like volume times molarity, get moles, and then multiply by the molar mass. But here it's already made into a solution, and we're just diluting it and making it a dilute solution. Okay. Okay, we're going to go through this very quickly. We're going to stop at precipitation because that's what we're going to do tomorrow. So this is a very quick review. Synthesis and composition reactions. Remember, we're doing two more simple substances to form one more complex substance. It's not always an element plus an element makes a compound. Sometimes it might be two simpler compounds make a more complex compound, so you got to be careful of that. Okay. Right off the bat, if I mix a non-metal oxide with water, I form acid. Okay. If I do a metal oxide plus water, I make a hydroxide. Okay. But they're going to be making one product. Okay. Decomposition, or the exact opposite. I've got one reactant breaking down into two different simpler substances. So in the case of water, if I decompose water, I go back to hydrogen and oxygen atoms, or diatomic molecules. In the case of like a perchlorate or a chlorate, or they break down back into their elements, or they could break down into, like carbonates will break down into CO2 and the metal oxide. Okay. We don't deal with the simple ones like that much. I want you to recognize them from Chem 1. We're going to be doing basically precipitation, acid base, and redox. Those are the three that we care about. Okay. Single replacement, of course, is when you have an element plus a compound. Remember the activity series where you would check the activity series and say, will this replace this? If it was below it or whatever. The good news is, assume they replace. AP is not in the business of giving you no reactions. If they're giving you a reaction, it happens. Okay? Because how can they ask you further follow-up questions if it's not happening? So assume the reaction happens. So I don't even give you an activity series. You don't need it, because if I'm showing you a single replacement, it happens. Okay, wow, that came a lot easier. And then double replacement reactions. There are a couple of different kinds of double replacement. So we're not just, when we did it, we thought, oh, double replacement, it made a solid. Okay, remember, double replacement can also produce a gas or a pure liquid in the case of like acid-base reactions. Okay, and that's the general formula. They're switching partners. Okay, and then of course combustion. In Chem 1, we learned that all combustion makes what? CO2 and water. That's not true. It was for Chem 1 because that was easy for y'all to remember, but there are other ways to combust things. And that you kind of saw that when we were doing the empirical formulas. If there was nitrogen present, it could make nitrogen oxide. If there was sulfur present, it could make sulfur oxide or sulfur dioxide. So here's what I don't want to see. I don't want you to say, oh, magnesium plus oxygen, that's combustion. It makes CO2 and water. No. Okay? So keep that in mind. So really and truly, what we did in lab yesterday was a combustion. Also part of a single, off a composition because we made magnesium, oxygen, and magnesium oxide. But technically, we burned it, right? We combusted it. Okay? But in Chem 1, that confuses kids too much, so we just say everything makes CO2 and water. Not anymore. So in Chem 1, I tell you stuff to like make it easier for everybody to get for the masses, and then in AP, you learn what it really is. Yeah. Like that you can balance equations with fractions. I didn't tell y'all that in Chem 1 because it blows people's minds, but y'all are mature enough to have your mind blown. Okay? And also, when we have a combustion reaction, we're not literally burning things every single time. You have combustion going on in your body right now. Right? Cellular respiration. And that's where we're stopping. Boom.